Hey, good afternoon. My name is Doug Matzke. I work in Dallas, and I'm with Z Omega, one of the PyTexas Diamond sponsors. This is my first time at a PyTexas workshop, but I've been using Python for a while. My introduction, I've actually been programming since I was in high school, and since that was in the late 60s, that was unusual at that time. But my focus lately has been on dynamic languages, and I like any language that has a val in it, except Perl. Okay, but I've also been programming for 13 years in Python and another 10 years in Lisp. So I come from a functional programming and function and object mixture from Lisp. So working in Z Omega since January 2014, but my hobby is PhD in quantum computing, and there's going to be a lightning talk about that, one of my programs later this afternoon. And you can also see my website for a YouTube video on that, quantumdoug.com. So fun stuff for me. So I do that instead of golf. Quantum computing instead of golf. Hey, so what we're doing at Z Omega is a project called ClicBank, stands for Clinical Content Bank, and what we've decided we needed to do is put a distributed version control system in our application because we had sort of a primitive one already built in. So what we're going to do is show you that we decided to use Git, and this case study basically describes what we're doing and thinking about that and what the design looks like and things like that. So we'll go through details as we go here. So this is what the application looks like. We currently have an application called Jiva, which is in the software for the medical insurance industry. And so one of the things that this application does is allows our customers to create their own assessments of their patients. So they can say, do you smoke? Are you overweight? That kind of stuff, and catalog those answers. And so they have these assessments with questions and answers, and then they have all this other stuff related to what their plan of care that they should recommend. There's templates, and now they have groups of questions called question and answer groups, and other things, actions, sentinel actions that they can do under certain conditions, then go do these things as follow-ups. So it's a pretty complicated system, and in general, you can think of this as 20 to 50,000 different little definitions, little entries in a database table that have a very primitive version control system behind them. So ClicBank uses these, and part of the problem is they're using a regular database and they're pushing these definitions between different installation machine sets at the customer site, like dev, UAT, productions. And the problem is that we have a simple database version control system. It has draft, published, archive versions, and IDNs to track what's the identity of these objects. And so storing them in a SQL database tables. So what we want is a full-featured distributed version control system. So as we move these definitions from one machine to the next machine, that we know that which definition is it, that it has actually a unique name and we get the right one. Otherwise, you can accidentally wipe off one object because its IDN doesn't match that on the other system. So what we want is this distributed version control system, and we want to have a unique ID, UUIDs, and we want to be able to have all the other features that you would expect for distributed version control, like repositories, pull, push, tags, branches, merge. So what we're going to do with ClicBank is to use Git so that we don't have to rewrite all the software, all the merge software, all the pull requests, all that kind of stuff, that we don't have to rewrite all that. And so the goal, in order to be able to use any kind of version control system that's off the shelf, we obviously have to have source definitions for every object type, for every entity type. And so we chose XML as our files, and we'll actually store files in a file system, or they can be virtualized where you just send them right to Git as open streams and in and out of Git. Those are two choices. And then we use Git as an open standard. Okay, so here's like I said, I mentioned the version controls, the current version control system. They have draft, pending, published, archive, and deactivated. But what they're missing is the UUIDs, the forks, the clones, the tags, the branches, push, pulls, merges. So you see there's a lot of things that they're missing in their version control system right now. And we can map each of these two things in our new design. So that's the key. So, Git, for those of you, most probably everybody knows Git, but here's a little Git 101 railroad tracks, as we call it. Essentially, you start with a master repo up here, and I don't know if it shows this, master repo up here, and then what typically what happens is you branch it, or you fork it, one of the two, and you end up with a version of the database that you can then clone over to This green box here on the bottom is essentially your local workspace, the get client part of it, and the blue box up here is essentially the get server part of it. So think about, there's two halves here. This is the safe up in the sky that has all the server repos in it, and this is the one you're actually going to be modifying down here. So you would clone it, install those definitions from the files, you would modify those files like you were editing them, but you'd be using a UI to do that, and then you would change and you would commit those and tag them and push it. And then you do the pull request, and then you could potentially use those definitions in another part of the system. So that's the general flow, and that's a normal Git flow. So I mean, that's any kind of version control system flow. But the difference here is, in this particular case, our strategy is both the server part and the client part are both in the cloud. So if you saw this picture here, we're actually going to have one repo. This is the server part up here. This big yellow box represents ClicBank, and it's going to have what we've coined the term as a workspace. Essentially, it's the get client part of the Git, and it has these files here, which are the XML files. And so we can create a branch for Workspace, and this Workspace is the part where we can edit things, change things, and this is the sandbox. Okay, and then these users can either share a workspace, kind of like a Google Docs, or they can keep separate ones. You know, like this would be like on, think of it as a separate machine. I have my own copy of everything. And so you can do both of that, and essentially every workspace would be fronted with a branch, so every time we change something here, we can safely push it to the branch and not have to worry about running into each other. So this is an important step here, this piece, this Google Docs style of interaction, because our team is distributed both in the US and in India, and so we may have multiple people working on a design at the same time, changing definitions simultaneously, just like you would on a spreadsheet in Google Docs, and they want to be able to see those updates instantly. So this is what we're doing from a design. I'll show you more details about that. But also then we're going to have a push-pull strategy, pull and push strategy, where every time you make a change here and you commit, it automatically gets pushes to the branch. So we're going to hide these get operations behind the facade of our application. And the commit is important because those messages ultimately go to the customer that says, what things have you changed in the definition since we last got your update? So they want to see those. So, and then tags can be manually initiated and pushed as well as to the remote. So our merge strategy is to do the pull and merge on the Git server and have entity level merges. In other words, we're not going to do line merges. It doesn't make any sense to replace one line in an XML file because it might not have any contextual meaning. So the entities are pretty small, and you'll change the whole file or none of it. And that's the strategy for pushing for the merge strategy. We currently have the batch import and commit strategy figured out already. I mean, what we found out is if we tried to do a commit on each entity, we have 20,000 to 50,000 files out there, little XML files. If you do it on per file basis, it's too slow. The overhead to get into Git and out of Git for each file is too slow. But if you say, do this whole folder, it goes bloop, fast. It's really fast. So, so we found that out early on, and so we have essentially the files broken into domains of files, and that's important because if you're going to be cross-platform dependent or independent, you want to have like less than 10,000 files per folder in a Windows system anyhow. So we broke them up, and now the system looks, you'll see here in a minute what that looks like. And then an automated commit message is automatically created every time I import a file. So a lot of these automatic things are automatically done. So then the interactive edit and commit strategy, entities can edit these XML file and leave those changes as draft changes. So the file can be changed but not committed. And then they'll see this as a list of changed files for that repository, and then they can decide to selectively commit some of those when they're ready for them. So the file change is denoted per domain folder, and you can initiate explicit commits when they're ready. So that's not much different than what they're currently doing. They have to publish definitions in their current system that they're using, and so this publish is like a commit in the system. And we eventually will allow both deletion and deactivation of these entities if we're not using them anymore. So one more slide on the workspace, and then we'll show you some architecture diagrams here. But essentially what a workspace is, it contains a set of entity XML files. Each file is going to have its own unique identifier, which as each entity is born, it creates like a social security number. UUID is created at that time. and that way you know we actually have an entity in place. And then we keep track of that in a persistent way, and then we keep track of aliases to that, so if somebody says, give me the object with this alias name, it knows that that's the equivalent object with that type and that name. So the other thing is we have a notion of reference objects, so that you can order these things out of order. So you can say, I want a reference, an object with this alias, but I haven't seen that object with this alias yet. So it's a reference that's not been fulfilled yet. Later on, that definition comes in, it makes the link, and now it's a fulfilled reference, and so it's not missing anymore. And so now we can load these files in any order, and we don't have all these dangling dependencies. That's a real problem in the database, because essentially you can't reference a foreign key unless the other key is already there. So this solves that problem. Import and export and edit things are all going to be idempotent, which means if you do it more than once, you'll see it as if you'd done it once. So those are a few more details. The other thing is when we actually do the editing, we're going to have this Google-style thing where we say edit. It'll automatically lock it. We can save it. We can cancel it. We can say done. It gets out of edit mode. And anytime we do a save, anytime we change an XML file, that'll be propagated through async messaging to the other users. And so that's part of the edit design. So I mean, it's a Google Docs style with Git repository in the back end. So that's sort of the design. Here is the file layout. I'm going to show you here. Just look at this big one here, the large one first. Think if you have a workspace and each domain, there's a subsystem folder. Like this is for the assessments, ACE. This is for the plan of care. This is for the Sentinel actions. This is for other things. And each folder has another subtype of the type of entities that are in there. For instance, assessments, questions, attributes, groups, care plans. And then each one of those has XMLs where the UUID is actually the XML file name. So that way we can instantly find a file by a specific UUID based on its file name. So and these can support drafts because this file can just be changed out there, no big deal, and Git knows that something has changed. And then we have multiple, each workspace has its own set of copies of files. Think of this, normally this is on one machine and this is on another machine, but since it's in the cloud, we'll all have these different workspaces that each has their own unique name, and then we'll have a separate copy or a clone of those files. So you have multiple sets of files to work with, if that makes sense. So that's the kind of at the bottom, the physical layer. And then, so what about the XML? Do we have any requirements on the XML? Yeah, each entity object, I mean, if you think about what a class is and an instance of a class is in Python, it's really a typed dictionary. So it's a type of a dictionary, and then it has key value pairs, which are the instance variables of that class instance. And so essentially that's what a dictionary is. So essentially what we're doing is we can save out any of these Python objects, which are going to be Python entity objects. There's a class for each one of those. We can save them out as XML, just using as dictionaries, but in an XML format. And we're going to be using, I'll show you in a second here, an example, a type-based, tag-based approach for the output. We're not using a lot of attributes. The attributes are more for the parser part of itself rather than the content. And you'll see that that works pretty well. And then we're going to pretty print it so we can easily see what's in there during development. It's about 25% bigger when we pretty print the XML. And then I do an inverted sorting of the field, so the field order is repeatable. And it just, by redoing inverted alphabetic sorting, the UUID ends up being at the top, and we can see it easily, and it works pretty well. And then we have all these subfolders that look like this, where you have, like I said, the workspace name, the domain name, the entity type, and then the UUID. That's what the path looks like. The same save and read XML code is used for all entity types and primitives. In other words, this is not programmed per entity type. It's very generic. It's only a couple hundred lines of code for all the read and write, and I can do complete XML loopback on itself, and it says what I wrote and what I read is the same. So I can do that for all the entity types. And what's interesting, this approach, using entity objects as nested dictionaries, is the same thing that allows us to do JSON as the XML code. So the JSON code is in that 200 lines too. Essentially, we can produce nested dictionaries, so the same object, essentially it's multiple representations. We have an entity instance in memory in Python. We can save it out as XML as one representation. We can save it out as another representation as JSON, and it's basically nested dictionaries. It's all the same representation with different syntax. Okay? So here's what an example of the entity XML looks like. First of all, you're going to have a tag, and usually we have the goal, the type of object is the goal. Is this example here, it's an entity called goal. And this is the one place where we put the attribute. We just use it for my parsing. It's the class entity. So there's the top tag, and then beneath it are the subtags for each of the instance variables. So this is the keys of the hash table of the dictionary, okay, in an XML style. And then what you do is you can say, here's my name, my UUID, and that's the hex version of the UUID. This is using UUID4. In the Python UUID package. And then what we can do is we can say, here's the value of the title tag, which is another instance class called languages, and it has submembers as well. So this is every other cycle. The first one is the class, the next one is the instance variables, and below that is another class, and then its contents. So it's even and odd like that. And then finally, here's a reference to another object, a goal class. A goal points to a goal class. It's like its parent. And so here's a reference, and it says, I have a goal class, and it references a class of this name, and it says it's a reference class. And this is the alias here. I'll show you here, the alias. And then this is the UUID, and the fact that I know this UUID means I've found it before. If I have this missing here, it means I haven't found it before. So I can actually save XML files with missing references, and then when I load it later on, I still know it's missing. So that's handy to be able to do that. So, and then again, the same nested dictionary approach works for JSON. So this is probably a little bit different than most hand-generated XML, but the goal is programmatically generate all of this, and programmatically read it, and don't have any custom code in here. Basically, you just have roots. All the class types, and then you have the leaves, which are these things that you're seeing here. Okay. So we showed this picture before here, but another way to look at a workspace, it's a clone of a Get repository branch. Remember, we talked about it as a set of XML, but it's also a clone of a Get repository branch. So each repository has read and write access control per user or per group, and each distinct workspace has its own branch of the main repository. And each workspace has a set of client files checked out. So you could say check out a particular tag. So you could look at an older version if you needed to. And each workspace can be shared by one or more users like Google Docs. So this is the grand design here. And again, the picture, it's another way of looking at how workspaces and repositories are related to each other. So let's talk about the architecture. So here's ClicBank. It's the big box in the sky. This is all in a cloud environment, okay? We're going to have, as a part of that, it could be on a physical different server, but here's the get repos, the get server part of it. It's going to have the repositories, the branches, the clones, the pulls, and the pushes, and the pull merges, okay? So then the next thing we do is we say, okay, now here's the workspace, which is the get client part of it. It has the workspace concept, the clone to local files, the commit the changes, tag the latest files, and push back to the server. So this is where all the action happens, where the Git repos are up in the safe in the sky. The next thing we're going to do is we're going to have Pyramid running Python services, and it's going to interact we can use XML to talk to this local file. So the code, the engine part of the code, is written as part of these Pyramid Python services as an API that they can call, and they manage the files to the disk and the XML and the Git. Okay, and then we can create this import-export facility that is, again, part of this engine piece, and we have this piece, we have what you see here working except the repo part already working, where we can import and export import into XML files and create all the Git stuff. So we have statistics for that. And then eventually, you can have other services, like for instance, we're going to have lock services and things like that, because when we add the UI, we have to have async messaging, and we're going to have this JSON being passed like this. So this is how the pieces evolve over time. And we basically have most of the pieces of this beginning to run, and now we're filling in parts of the parts that are missing, like the other services, the locking mechanism, and the Git repo part. So those are the pieces we're working on next. So some of our design choices is, hey, we wanted portability for Linux and Windows. So right now it's running both in both systems that way. We're using Get Python as a Git module that we're using, Python module, and works pretty well on both systems. In knowing that Git shell works slightly different on Windows than it does on Linux, so there's just a thing that we have to work out if there's any incompatibilities that we haven't seen yet on that. We're using AngularJS and Pyramid as our UI and web framework, and we're going to do this Google Docs style for distributed entity sharing, and use these service-oriented architectures with RabbitMQ for queuing up these things, and async messaging as well, where we've chosen Stomp as our async messaging framework. So the Workspace concept seems to be working. I mean, everybody in our project seems to get it. It seems to be intuitive, calling it a workspace. And we're going to have all these services in that picture we showed, including Mongo, document management system, a lock service, authorization token service. Also, we expect to have Zio and ZioDB for Python instance sharing across multiple servers, and using this open source Git server. So we still have to pick which one we're doing for that. But here's the sort of another view of that same thing. If you look at, there's these two entities. I mean, ultimately, we sort of right now are working with just one of these, but ultimately, if you have enough users where you have to have multiple services running either on multiple CPUs or multiple machines, you're going to have this version of the service and this version of the service supporting a bunch of clients. And essentially, you may have the same entity X in both of those, and they'll both be sharing the same XML file because it's the same XML file in the same workspace. So we may have, using ZioDB to keep these two copies consistent, and we'll be using messaging to do this, which means that we'll have 5 representations. We have the Python instance representation, we have the XML files versions, we have the Git format version, we have the pickle version for ZioDB, and we have the JSON version. So as you see, as you keep adding these requirements, you have 5 simultaneous representations of the same data, so you want to kind of keep it simple. So that's what we've done. And every time you do a ZioDB, every time you commit XML files, you also do a ZioDB commit. So commits kind of happen at the same granularity. Okay. So that's that picture. So let's talk about the performance of this. Like I said, we have an example that represents like all 50 assessments that are currently part of the standard set of assessments that we are looking at content providing to our customers. And so altogether, that represents about 21,000 entities in those 50 assessments and everything they point to. So it's on my personal, just to give you a sense of what this machine I'm using here for this PowerPoint presentation is my personal development machine. It's a Windows machine with 8 gigabytes of RAM and solid state disks. It also has a VirtualBox running CentOS version for the Linux. So I can test both Python and the Windows and Linux environment. So the entity import performance takes about 3 minutes to load the about 12 files that we have that has the 21,000 entities in it. And probably the longest time is just writing the files to the disk. So as we may try to virtualize it and not physically write them to the disk, just write them right to Git, and Git's sort of compressed version of that means less to the disk. So it may speed it up by that. We're not worried about the time, because for 3 minutes, we're going to use async messaging, and we don't import that often, so this seems like a reasonable amount of time. Linux seems to be slightly faster than Windows. I'm not sure why that is. And the Git commit for individual entities was too slow, so we did it per directory. But think of it as we would have a maximum of 50,000 of these entities per workspace, and maybe eventually we would have 10 to 20 active workspaces in the system. So we just have to figure out the total amount of memory and the total number of users we would use, and the total number of disk space. So that kind of puts an upper bound on those. And we actually have a ZioDB and a Duris ODB prototype, so that we can just plug that in and compare what the file sizes are for the pickle part of it as well. So we're working on that part as well. So this is what the metrics were. Here's the example of that. We're using a Workspace, and it has an encoded name, so we don't have to worry about characters. And then you see these folders. Here's the assessments. Here's with its entity types. Here's the code tables, which are a different kind of configuration item. Here's the plan of care with the goals and goals class that we talked about. And so if you look at this, if you look at just the whole repository sources, it ends up being about 54 megabytes for 21,000. If you look at just the these highlighted ones here, they're about 42 megs. So altogether, the XML is about 42 megs, the get is about 12 megs, the ZODB is about 116 megs. So we're total, for the total 21,000 NDB is about 170 megabytes for storing all this data. So that gives you a sense of the size of it. And again, the XML would be 25% smaller if we got rid of pretty printing out of it. Okay? And potentially we could get rid of the XML completely, like I said, if we decided we want to directly go to the Git as a stream, using a stream interface rather than as a file interface. So, okay. So, so the project status, we've got the local commits using the Git Python module. The workspace code size, the entire part of the engine that's dealing with the importing and the workspace management and the repository is 5 to 6K lines of code. It's not that big. I mean, we're trying to leverage object-oriented programming to the max to reuse this code as much as we can and reuse methods and stuff like that. So it's pretty small. It's complex in its design more than it is in its code size. But it has to be programmable so that we can create all these customized entity types. We probably have, right now we probably have 20 different entity types, as you could see by the number of subdirectories in the previous slide. But we're going to have 150 code tables, and each one of those is a custom class, if you want to think about it that way. So with its own classes for each, so that each one can be distinct from the others. We're currently choosing the branch and the remote and how to deal with branches and the API for that. And we want to create an API from these remotes. There is no API standard for this. Like if you go to api.github.com, you see one standard. If you go to Gitosis or Gitorius or whatever, they each have a different API for, like, list me all the workspaces, list me all the repositories on in your Git server. Those are not standardized. You can't find those using the Git client. So there's some apart. If you're trying to automate this stuff, you want to standardize on what those other APIs are, and there is not a standard right now. So hopefully the community will realize that other people are going to try to do this and promote a standard just like there is for the Git command line. So selecting the Git service as our choice. We have a problem where, you know, we're not going to have that many users because we'll probably have a Git server that just has a couple logins, and we'll be using our application as the proxy in front of it. But the problem is that most professional Git servers, like GitHub itself professional or Bitbucket professional, they don't want to relicense it. They don't want a VAR relationship with us. So we don't want to have a small valued item, even though it's professional, releasing to our customers where the customer has to go and get a license from as a third party. It just doesn't make any sense. So we're probably going to have to go with a true open source version of the Git server as well. And the key thing there is what database they use. So we're looking at a database right now that uses Mongo as its, not as the repository part of it, because it's still using files for that, but as the overhead for saying what are all the workspace, what are all the repositories and that kind of stuff. So, so that's what we're looking at for the server. So I don't know what time we have here. Stash, we can't get a licensing. They won't. Essentially, we're violating their license by putting it on a third party. And even though it's really inexpensive for how we're using it, it'll be $100 a year or something like that. It's the licensing requirements that's the problem. So Bitbucket, which is the Stash, is Bitbucket's version of it. Yeah, we've already just checked them off the list. Same with GitHub. So they like someone to use it where they have, 500 logins and they get $10 a month for each login. That's where they're making their money. So, okay. So, like I said, I don't know what time it is here. Let's see what I'm doing. Yeah, I'm running pretty fast, faster than I expected, but so we'll have plenty of time for questions here. So here's the summary of the talk. Basically, we're going to be doing both the Git server and the client in the cloud. We're going to use these commits and tags with auto push. The workspace concept seems to be very useful. The no Git server API standard, that's a problem. We're going to be using async and RabbitMQ. to do this so that it's a Google Doc style. Performance seems satisfactory for everything that we've seen so far. Even the ZODB test that I've done says that basically the ZODB is done in parallel, separate processes, and it's almost invisible when you turn it on. And for the number of entities that we have and the file sizes we have, the embedded Git seems feasible. I mean, normally you would be storing these blobs in databases, but you have to manage the blobs in the database with the get requirements. So putting it in the database, unless Git stores it in a database too, you can't connect the get requirements and the database requirements. So maybe somebody will figure out a solution for that, but this seems to be about the right balance for what we're talking about here. So I think that's a summary of the talk, and I think that's my last talk. So does anyone have any questions? I mean, it looks like we have time for some questions, and it's been an interesting project because it kind of warps your mind about saying, oh, okay, they used to do it this way, now we have to do it this way in order to get these additional distributed version control systems. So has anyone done something like this before, or tried to do something like this before, or, okay, and have you picked a different Git server that you liked before, or something like this that you know about?
It actually wasn't Git-based, it was Alfresco-based.
Fresco, okay.
Alfresco being a document management system.
Okay.
It solves a very similar problem, versioning, specific workspaces, user control. The workflowing is configurable, which is either awesome or horrible, depending on how you do it.
Yeah.
Out of curiosity, have you run into any non-standard workflows that you've had to kind of code around?
Well, so far we're in the early stages of this development, essentially, that we haven't, quote, defined workspaces. I mean, they have workspaces in mind, but we're not going to program them. Now, what we'll do have is we'll have best practices, and their teams will be trained with workflows. But it's like, do they enforce a workflow for Git in general? No, most developers don't, right? It's sort of like, well, we do this, and then we do this, right? You make your changes, then you publish them, or we'll commit them at this point. And then there'll still be somebody who's in charge. Every team has a merge master, right? You don't let anybody merge, right? So we'll have a merge master here for this too, with certain authorization that nobody else does. And then and knowing that we can always fix everything because there's files everywhere. If we had to, we can go edit the files and fix them and get them back out there again, So, I mean, we have sort of a backup, merge complexity can grow depending on what you're doing, but the goal here is, eventually we'll have to figure out, well, we probably want rebase in there. So the complexities of all the merge complexities, we're just going to get started to get into it now. But the other thing we know we're going to need, and I forgot to put a slide about this, is how many of you know that Git has sub-modules, right? Right? A few of you know. And essentially what that is that you can say, I can have a super repository, and that has a bunch of dependent children repositories. And so when you do a get, you're actually doing pull. Think of it as build for Git, where you do the pull of the master, and it pulls all the sub ones underneath there too. So if you do a commit, you're actually committing it to the subordinate submodule, and then so that anytime you pull the master, you get those changes in the small. So you kind of break up the Git commits into each of the submodules that actually own it. Okay, so we sort of have a need for that in this case, because we have this thing called code tables. Think if we have a set of standard code tables for this application space, it's the main configuration data that's part of our application. What would happen is we would have like 200 of these code tables and maybe another 20,000 to 25,000 entities as a result of all these code tables. That's one of the next pieces we need to do. But we need to share those code tables with each customer. So what we're going to do, instead of doing submodules right away, what we'll probably do is be able to select a bunch of entities and essentially do copy and paste the entire definitions from one repository to another one, or do a fork to start out with those so that we can keep track of the history. It's the same UUID, but be able to know that then later on potentially we could do a remerge. So what do you call that when you merge just some of the definitions from another repository? What's that called, Jeff?
Cherry picking.
Cherry picking. Imagine cherry picking, but in an editor where you can say copy and paste these files or these definitions from one repository to another. It's kind of like cherry picking does, and then that way we would do that instead of submodules. But that's our initial thinking about that. But also we could do a fork to do the same thing, like pre-initialize a database that we know is going to be using these code tables as a fork, and then as a customer, and then we would be able to go and get those anytime, update them anytime we needed to. So go ahead.
So I might not really understand your problem there, but have you considered the subtrees for that? So there's a construct that gets similar to submodule, where a submodule pulls, basically creates a Git repository within your Git.
Yeah, that's what I was talking about, submodules.
Yeah. So what subtree does is don't quote me on this.
Yeah.
As I understand it, it's kind of like doing not a bear pull, but squash. So you define your subtree, and what you can do is that follows the your command Git repository.
Yeah.
And you can say pull all the subtree information,
Uh-huh.
and that will pull a
Subset?
yes, a single copy of that upstream repo.
Oh, okay.
In that upstream link,
Uh-huh.
it's just that single copy, so you're not, when you go in and commit to your repo,
Yeah.
you don't have to worry about the Git submodule that it's on the Git entity.
Okay. Okay. I mean, part of the problem is if they change something, let's say I did a fork or a copy, and then I change something, I never want to push it back because that's touching the master part of it, that we'd be using for everybody else. So we want to be careful about whether we're truly copying it and creating another fork, or whether we're really containing the link back to the original one. So we have to figure that out ourselves. We haven't gotten all of the detailed use cases for those figured out yet, but the ones that I've showed here, we do have use cases for, and we know that it's still cloudy about, it's in the cloud, of course. It's cloudy about what we're going to do about how we pull in these definitions and share them across multiple repositories. I don't know if anybody has experience with doing similar kind of thing and wants to talk to me about that. I appreciate picking your brain about it, just because, and that might be a good thing for me to go check if there's a fork, or would you call it a fork? No, a tree? Subtree, okay. I'll look to see what that. Cherry picking seemed like the one that's closest to what we're thinking about. A partial, pull some of the definitions, but not all of them, from another repository. So we're still going to have to work out this, but the key thing is all of this has to be done where you don't have a human there doing it. It's done from a command line, and then it does it automatically in the background. So go ahead. Right.
Have you considered writing your own course and using the plugin? Forget about the existing servers.
Well, yeah, somebody said that there's a version of the Git out there that kind of knows the internal structures, that we could, since it knows the internal structures, we could use the Git client and the Git server to do essentially using the same data structure. So the thing is, we're trying to use it as an open source package so we don't have to rewrite anything, So, I mean, if you have a recommendation about
Other servers.
Pardon?
There's several other servers that you can use.
Yeah. Yeah, I mean, I don't want to rewrite merge, a Git merge essentially. So I'd rather use that stuff off the shelf if we can find the right mix. So I think we're looking at, what's the one we're looking at right now? I forget which is the sort of the lead one that uses Mongo right now. I haven't worked on it all week because I came to the conference here and I can't remember the name of the leading choice that we're looking at right now. So, okay. Hey, I appreciate your attention today, and it looks like we're still going to get out a little bit early, but if anyone can offer other advice, please come on up and give me your suggestions. But we're trying to push many avenues here at once at Z-Omega, and we're kind of also trying to lead. We're trying to put all these advanced technologies sort of to lead the charge for applying these technologies to some of our other products. So we're purposely kind of using async messaging. We're purposely trying to use the Stomp. We're purposely trying to use the integration of those in this using AngularJS, and we're purposely trying to use Pyramid and getting away from Zope. So those are purposeful things that we're doing as part of moving our technology from where it is currently to where we see the future going. So this has multiple goals for this project, including the distributed version control system. So yeah, so it's an interesting project, and we've got some talented people working on it. And of course, Jeff is our leader on this project, and he has the vision for it. So we're trying to make it happen for him. So hey, thanks a lot for your time today, and appreciate your feedback. Thanks.